Hi, my name is Marco, and in this video I will try to argue that genetic programming is naturally suited to evolve bagging ensembles. So let's get started with our typical supervised learning setting where we have some training set and we have our features and our label, and we want to find a model that minimizes some error, which can be, for example, the mean square error. The error can be nicely decomposed into a few parts. One is called the irreproducible error. It has to do with the noise in the dataset. And then we have a few more parts. The bias is basically a measure of, on average, when we have a different realization of our underlying function f, how different is going to be in the model from this true function. And the other one is the variance, which is across different realizations, how different are going to be the models we find. And turns out that, of course, if we reduce either of these terms, we can then reduce the error. And bagging is a technique to reduce the variance term, which works as follows. What you do is you sample different realizations of the same size of the original dataset with replacement, though, and these are called bootstrap samples. You fit respective models H1 to H beta, say you have beta of them, and then you predict using something like the average or majority counting. Several works in literature have already successfully combined bagging with genetic programming, but I would argue that there is a research gap. So let me do a bit of a review about the state of the art. And let's start with classic GP. So in classic GP, what we do is to have a population of models, P1, 2P, and POP. And these models undergo variation or reproduction, call it as you prefer, to get a population of offspring. And then the offspring and optionally also the parents undergo selection to identify a new population, and iteratively you keep repeating this process across a number of generations. At the end of the process, what you do is to take the one single model that performs better as your final solution. So a natural way to perform bagging using genetic programming is to simply repeat the number of evolutions that return you every time a single model, using a different bootstrap sample every time to find a different model. And then you get your ensemble, which is made with some aggregation function. So the classic one will be take the average, but this works. For example, look at using something that is more interesting here. And then we have other works that try instead to perform bagging in one go. So out of a quick and efficient single evolution in genetic programming instead of repeating many evolutions. So for example, the work by Wang 2019 tried to identify niches in the populations and get models that are good from different niches to find an ensemble. And additionally, every generation, the data set is sampled anew to improve diversity in the process. Another work is the one by Grandick, where you have that your population is arranged spatially according to some graph structure, and there are clusters where a bootstrap sample is in the center of the cluster, and population members compete to be good according to the bootstrap sample. And then your sample is going to be made from the best models found across different clusters. And for example, one more is the work by Rodriguez in 2020, where they co-evolve at the same time your models, but also your aggregating functions or ensemble types, such that some models will belong to some ensembles, and at the end of the evolution, you return the one ensemble that is performing best. So in summary, what we have is that there are simple approaches which are easy to use because the moment you know how to set the hyperparameters of a classic single model GP evolution, those are probably going to be good hyperparameters also for the bagging process, but it's going to be expensive because you have to account for beta, your ensemble size, evolutions in total, and the cost of one evolution can be thought of to be like something like your population size times the numbers of generation times L times N, where L is the model size and N is the number of observations in your dataset. On the other hand, then we have these algorithms that are more complex but are fast. So their cost is going to be cheaper than repeating evolutions, but they come with a new mechanism and related hyperparameters which need to be tuned. So that's not maybe as simple as using something like classic GP multiple times. So this leads me to the research question that is, can we have, instead of these two approaches, something that is in between? So a simple genetic programming algorithm that can still be fast in involving bagging ensembles. So our goal is, given something that looks like classic GP, be able to obtain an ensemble in one go, in a single evolution of a single population. And all I want to do is to change the selection process. And I will also need to tweak the fitness evaluation to achieve that. So let me show you how this simple selection that is proposed in the paper works like. Let's say that beta is your desired ensemble size, and so you have your beta bootstrap samples. And now let's suppose that each model has beta different fitness values, each fitness value corresponding to one of the bootstrap samples. So what I do here is to extend truncation selection in a simple way, which is we take our parent and offspring population, we join them together, and then we want to select the new population out of this. And we do this by assigning for each jth, each of the bootstrap samples or fitness values that correspond to that. We get the top equal proportion of models that are good in that with respect to that fitness value or that bootstrap sample. So this is a very simple extension, I would say, of truncation selection, which guarantees a weakly monotonic fit decrease across all your bootstrap samples. It also tries to have this improvement that is uniform across the different bootstrap samples because of the fact that you are allocating the same number of models being promoted. And it requires no parameter setting within the selection process. Now, the problem here, of course, is that we have that each model needs to have beta fitness values. So a naive approach will be to recalculate the fitness every time for each bootstrap sample. And it turns out that if you do this way, you're going to incur in a cost that is no different from the one of repeating the number of evolutions multiple times. So a smarter approach instead is to recall that bootstrap samples are all realization of the original dataset, and therefore any observation that is in a bootstrap sample must be also an observation in the original dataset. So if you pre-store the collection of indices that identify a bootstrap sample, all you need to do is to compute the output on the original dataset and then reassemble this output according to your bootstrap sample. And so you're able to find a bootstrap sample specific fitness. It turns out that the cost of this is O big O of N beta plus L, which of course is smaller than big O beta Ln. And if we cancel out the n's and we plot this, we can see at a glance that this is going to scale much, much better. So this leads to this algorithm, which I call 2SEGP, Simple Simultaneous Ensemble Genetic Programming. It returns the end of the evolution ensemble that is made by the best found models for each bootstrap sample. It's simple because it's basically a simple extension of classic GP. It's faster than naively repeating evolutions by construction. But then now the question becomes, is this algorithm actually competitive with these more complex algorithms? So here in this slide, there's at a glance the experimental setup, which is mostly taken from the work of Rodriguez in 2020. There's one parameter that needs to be set for 2SCGP, which is the ensemble size, the ensemble size or number of bootstrap samples. And as a rule of thumb, in this benchmark, I use 10% of the total population size. There's more about this in the paper. And as datasets, I took the classification and regression datasets that appear in the study and are possible to find on the UCI repository. And then I compared with a number of algorithms, some of which I needed to rerun, some of which I obtained the results from the authors, and some others I took the results as reported in the paper. And the algorithms that are in this orange are ensemble algorithms, complex ensemble algorithms. All right, so what I would like to point out here is that basically 2SCGP is competitive. So these are test results for these classification data sets. You can see the accuracy, which is the median, and then the interquartile range. And the result is underlined if it's among the best ones in that there exists no other algorithm that achieves a statistically significantly superior performance. So we can see, for example, that M3GP here is able to outperform 2SCGP on this dataset, but 2SCGP remains competitive on 4 of the other datasets. In particular, is competitive when compared to these two that are ensemble methods. And then similar for regression, here we want to minimize the root mean square error. And we can see again that 2SCGP is competitive on these three. It is outperformed by these two methods here on ENH, but its score is not that bad. All right, so then in the paper, I discussed some insights. For example, what happens when beta changes and what happens if you try to do an ablation of selection and how a probability looks like across different bootstrap samples. Because of time, I need to I will just show a little bit of this one. And so here in this plot, I show the test root mean square error with respect to the average time taken by an algorithm to run. And so we have a few algorithms. So the black represents classic genetic programming that returns one model. In blue, we have a repetition of classic genetic programming in a linear fashion. So the 10th blue point will mean it's the 10th times we repeat it, and so an ensemble of size 10. In pink and green, we have these more complex ensemble algorithms. And then in red, we have 2SEGP. But here I'm scaling the ensemble size in an exponential manner. So actually the last point has 500 members in the ensemble, and the first point has 5. So we can see that even if we scale it exponentially, the running time stays quite small and not far from the one of the other complex ensemble methods. At the same time, of course, you can see that an ensemble of size 10 with repeating evolutions is pretty good compared to, let's say, an ensemble of size 100 or 250 with 2SCGP. But don't forget that to get this point, we have seen 10 times the population size that 2SCGP has seen instead. So in conclusion, in this paper, I try to argue that bagging comes almost for free when we do genetic programming. And it's easy to transition from a evolution that gives you a single model into one that gives you an ensemble in the bagging setting. All you need to do, in fact, is to compute fitness value for each bootstrap sample and have a selection that tries to promote the population to specialize across to the different bootstrap samples. And in fact, many algorithms that give you one model can already be changed a little bit so that you can obtain a bagging version of them. There are a few limitations. For example, in the paper discussed the fact that selection pressure increases with your beta, your ensemble size. So maybe there's something we would like to do there. And another problem is that if we evolve an ensemble, we don't anymore have a single model, so interpretability is lost. However, we have also some pros. That is, for example, when we use ensemble, it's quite easy to get good uncertainty estimations. And another thing is that much of this recipe actually goes beyond GP. You can use it also, for example, near evolution if you wish to. I would like to finally acknowledge Nuno Rodriguez and colleagues and Grandic for providing results that allow me to run some of these comparisons. And I say thank you once more to Grant, as well as to Eric Medved and Matthias Wade for insightful discussions and feedback while I was preparing this paper. Thank you very much for listening to this talk.